Almost every biologically significant reaction is governed by an enzyme. I'm Tyler Farah, and in this lesson, we're going to look at two different ways of plotting the activity of enzymes. Scientists quantify enzyme activity using two numbers, Vmax and the Michaelis constant, Km. They also plot enzyme activity in two different ways, the Lineweaver-Burke plot and the Michaelis-Menten plot. Therefore, in this lesson, we're going to look at how these two plots compare and contrast and how we can find those important numbers, Vmax and Km, on each one. To explore these different ways of plotting enzyme activity, we're going to take a look at a question involving drugs that you may recognize as being commonly prescribed for managing cholesterol. Take a moment and read this question stem right now. One interesting aspect of this question stem is that all three of these commonly prescribed drugs are competitive inhibitors of the same enzyme. So you can imagine different pharmaceutical companies each wanting to have their own branded competitive inhibitor that actually acts in kind of the same way. This begs a good question though. Before we dig into Michaelis-Menten plots and Lineweaver-Burke plots, it's a good idea to first understand what competitive inhibition is in the first place. So take a moment and in your own words, jot down what that word competitive inhibition means. To understand competitive inhibition, first we have to understand a little bit about enzymes. Enzymes are protein-based biological catalysts, and most enzymes have an active site that is custom-made for just one substrate or just a class of substrates. And a substrate will fit into that active site, whereupon the enzyme will catalyze some sort of a biological reaction. What competitive inhibitors do is block that reaction by binding to the active site first. Now, an interesting aspect of this that's going to come up later on in this lesson is that term competitive. Competitive implies that you can win. That is to say, there is a way for the substrate to overcome this enzyme inhibition. Think for a second and jot down, how can the substrate ultimately beat the inhibitor? In competitive inhibition, nothing has actually changed about the enzyme itself. It's just that the inhibitor happens to be getting to the active site first. So the way that the substrate molecule can win competitive inhibition is if you simply have more of the substrate molecule in the first place. That is, you can ultimately boost your reaction back to the same rate just by adding more substrate so that the substrate is more likely to bind than the inhibitor. While this question stem is technically about Lineweaver-Burke plots and how a competitive inhibitor will affect a Lineweaver-Burke plot, we're going to see that Lineweaver-Burke plots are kind of hard to understand. Now, there are a lot of advantages to Lineweaver-Burke plots, but it's a good idea to start with Michaelis-Menten plots. The Michaelis-Menten plot actually came first in science history, and it has a lot of advantages of its own, the first of which being it's pretty easy to look at a Lineweaver-Burke plot and quickly understand what's going on. For starters, you might imagine a scientist in a lab who has a certain amount of substrate and a certain amount of enzyme, and that scientist measures the resulting reaction velocity. And then you might think, okay, here we can increase substrate concentration on the plot by moving to the right along the x-axis. And what I'd like you to think for a moment and jot down in your lesson book is, how would this affect the reaction's rate? So if we are feeding the enzymes more substrate, we would expect that the rate would increase as well. Now, the interesting thing about this is that when you connect the dots, so to speak, on this plot, what you find is not a linear relationship. Rather, this relationship approaches an asymptotic maximum value that's often called Vmax, which stands for the maximum velocity. What I'd like you to think about next, and again, jot this down in your lesson book, is why. Why would this enzyme reaction approach an asymptotic maximum as we continue to increase the substrate concentration? In a test tube full of enzymes and substrate, you might have many, many billions of enzyme molecules, but ultimately you have a finite number of enzymes. And that means you have a finite number of active catalytic sites. There reaches a point where every one of those active sites at a given time is bound up with substrate, and the reaction simply cannot proceed any faster because the enzyme becomes a limiting factor in the reaction. So it's important to recognize that as we add more substrate concentration, the rate of the reaction continues to go up. We're never going to lose reaction rate. It's just that that reaction rate begins to sort of peak out at a certain point. Along the lines of quantifying how fast a given enzyme is, there's another really important number that we want to consider called the Michaelis constant. And I would draw an analogy to an automobile. If you want to brag about how fast your car is, there are two different ways you can do that. You could talk about your car's top speed, or you could talk about how quickly it gets to the top speed. That is, its acceleration. And I like my car for an example of this. It turns out that my car goes 120 miles per hour. And if you take half that, you get 60. Now, that's a great number because auto enthusiasts will often talk about the 0 to 60 time of their car. That is how long it takes for their car to get from 0 miles per hour up to 60 miles per hour. My car's 0 to 60 time is not that impressive, but you could imagine a really fast car would have a very small 0 to 60 time because that car would accelerate very rapidly, it would get going very quickly, and it wouldn't take much time for that car to get up to 60 miles per hour. Now, what does that have to do with enzymes? Well, the way that we quantify the quote-unquote acceleration of an enzyme, or how rapidly it gets up to its maximum speed, is we first take the enzyme's half max speed. That is, once you've determined the max velocity, that asymptotic maximum, you just cut that velocity in half. And from there, scientists will trace from the curve down to the x-axis, which shows substrate concentration, and this is Km, the Michaelis constant. This is a specific substrate concentration that is required to get that particular population of enzymes up to its half max value. And again, just like cars, the smaller the Km value, the more rapidly that enzyme is accelerating up to its max speed. Ultimately, for an enzyme that has very, very high activity, you would expect that enzyme to have a large Vmax value and a small Km value. By contrast, an enzyme that is not very active would have a small max value and a larger Km. So in short, Michaelis-Menten plots are a great way of demonstrating all of these quantifiable values and ideas about enzymes. But there are some difficulties with working with Michaelis-Menten plots. In fact, I can think of several. So what I'd like you to do is spend a moment and look at this plot and think about maybe one or two things that you can come up with that would make this plot hard to use. One thing that comes to mind when I think about difficulties with the Michaelis-Menten plot is the fact that this is an asymptotic maximum, which means that technically our plot should never actually hit that asymptote. I've drawn Vmax on screen, but it's really just my best guess about where that asymptote is going to finally land. And then again, if we don't know the exact Vmax value, we can't know the exact 1/2 Vmax value. And since 1/2 Vmax gave us Km, we can't know the exact Km either. All of these things that are found from this particular plot are really just our best guesses. Another difficulty with the Michaelis-Menten plot is the fact that it does have this curved shape. Again, if you're a researcher in a lab trying to generate one of these, you're probably going to need at least a dozen or so data points before you can feed that into some sort of computer algorithm that's going to spit out a reasonable guess of what this plot should look like. So while Michaelis-Menten plots are conceptually very nice, they are practically kind of challenging. We're going to take a look next at Lineweaver-Burk plots, which are sort of the opposite in every way. That is, they are conceptually a little bit more challenging, but they're practically a lot nicer, and that's going to earn us points on the MCAT. When I say that Lineweaver-Burk plots are conceptually much more challenging, you can see why right here and right here. Basically, what we've done is we've taken the units from a Michaelis-Menten plot and we've flipped both of them. For this reason, Lineweaver-Burk plots are often called double reciprocal plots. And the first thing that we have to understand about Lineweaver-Burk plots is how to even use them given this double reciprocal nature. So let's repeat the experiment from our Michaelis-Menten plot. Again, imagine that you're a researcher and you have a certain amount of substrate concentration and you have plotted that to the corresponding velocity. What you're going to do in this is you're going to increase the substrate concentration, and we already know that that's going to increase the rate of the reaction. But the question now becomes, where should our second data point be on this plot? In fact, go ahead and draw in the second data plot onto your own Lineweaver-Burke plot where you think that it should be, given again an increase in substrate concentration and an increase in corresponding reaction velocity. One way to conceptualize this is that we're going to be increasing the substrate concentration, and that means decreasing 1 over S. Therefore, we would expect that an increase in substrate concentration might track to the left. Similarly, for the reaction velocity, if we're increasing the velocity, we'll be decreasing 1 over the velocity, and so the rate should move down as we increase the rate overall. Another way to conceptualize this, though, is again, Lineweaver-Burke plots are the double reciprocal of Michaelis-Menten plots. They're kind of the flip in every way. They'll tell us the same information, but we're going to get it in a kind of a backwards way. The point is, overall, we're going to move down and to the left in order to accomplish that. Next up, we want to consider the kind of curve that actually gets plotted on a Lineweaver-Burke plot. So based on your previous studies, actually go ahead and draw in the kind of curve that you know you're going to find on a Lineweaver-Burke plot. And if you're not actually sure, that's all right. That's why you're watching this video. Just go ahead and advance and we'll find out the answer. Lineweaver-Burke plots form a straight line. This is one of the big advantages of a Lineweaver-Burke plot over that weird asymptotic kind of plot shown on a Michaelis-Menten diagram. But again, this has real-world practical implications as well, because it only takes 2 data points to make a line. So again, as a researcher in a lab, you can literally measure 2 different reaction rates corresponding to 2 different substrate concentrations, and voila, you've got your Lineweaver-Burke. Now, in order for Lineweaver-Burke plots to be truly as useful, or maybe even more useful than Michaelis-Menten plots, we need to be able to find the Vmax and the Km value on these, just like we could on the other plot type. So again, while this is a little more conceptually challenging on the Lineweaver-Burke plot, we're going to find out that it ends up being much easier to do in the end. To start with, if we want to find the Vmax value, well, we've got to find out where an infinite substrate concentration could be found on this plot. And the answer is actually at the y-axis, that is, as x approaches 0. Think for a second and jot down in your lesson book why we would find an infinite substrate concentration as the x value approaches 0. The reason why an infinite substrate concentration is found at the y-axis, again, has to do with the double reciprocal nature of this plot. If I increase the substrate concentration towards infinity, well, then 1 over the substrate concentration is going to decrease down to 0. So at the y-axis, we actually find a quote-unquote infinite substrate concentration. And so at the y-intercept value, we find not the Vmax value, but again, the 1 over Vmax value. On test day, if you're given a Lineweaver-Burke plot and you're asked what the Vmax is for a given enzyme, you just look at the y-intercept and then reciprocate that number and you are set to jet. Now, as for the Km value, things are a little bit more tricky. Lineweaver and Burke actually proved this mathematically using some pretty complicated algebra, but that's not as fun as the way we're going to find Km on this plot. We're going to do this graphically, and we're going to do it in a very similar way that we found Km on a Michaelis-Menten plot. Starting with, we need to know where the half-max value is. Now, given, again, that the y-axis is 1 over the reaction rate, and given that we now know where 1 over Vmax is, think for a second and actually indicate on your diagram where you believe that 1 over the half-max value should be found. The half-max value is actually found twice the distance above the Vmax value. You can think about this algebraically. If I put half in the denominator of a fraction, that becomes 2 times the fraction overall. So by having the Vmax value, we double the 1 over Vmax value. The point is, just like on a Michaelis-Menten plot, we've now found the half-max value on our Lineweaver-Burke plot. And so just like on a Michaelis-Menten plot, we can now track that down and find not the Km value, but the 1 over Km value. The location of this 1 over Km value might seem kind of arbitrary, but there's a really cool trick for this. And it has to do with observing the fact that the distance from the 1 over Km value to the y-axis is exactly the same as the distance from the y-axis to the x-intercept. So it turns out that on a Lineweaver-Burk plot, the x-intercept is the -1/km value. Overall, what we've seen is that Lineweaver-Burk plots, again, are a little bit more conceptually challenging. But once you figure out how to use a Lineweaver-Burk plot, they'll give you all the same information that you can get from a Michaelis-Menten plot, but actually a lot more easily. And because it's a straight line, these are much easier to generate. Now we get to the fun stuff. We're going to add an inhibitor and see how it changes things, both the enzyme's activity and how that shows up on our Lineweaver-Burk plot. First off, we're asked why a competitive inhibitor will change the enzyme's Michaelis constant, Km, while leaving its Vmax unchanged. Let's start with the second half of that question and actually jot down in your lesson book, why would a competitive inhibitor not change the enzyme's Vmax? Remember from earlier, a competitive inhibitor only blocks the active site of an enzyme. It doesn't change the enzyme or deactivate the enzyme. And in fact, we can even overcome competitive inhibition by adding enough substrate that it ultimately outcompetes the competitive inhibitor. So for these reasons, we would expect that the Vmax would remain unchanged. And what that means for our Lineweaver-Burk plot is that the y-intercept stays exactly the same. What about that second question? Why would a competitive inhibitor increase an enzyme's Km? And while you're at it, think about and maybe even annotate in your lesson book how that's going to affect the Lineweaver-Burk plot. Remember that Km is a number that tells you essentially how rapidly your enzyme accelerates up to speed. And just like a car and a 0 to 60 clock time, the lower the Km value, the better the enzyme is at accelerating. Well, now we have a competitive inhibitor, and it's blocking the enzyme's active site, and it's preventing the enzyme from binding onto and reacting with the substrate. This is kind of like getting gunk or engine slime in your engine. It's going to slow down your engine, aka your enzyme, and it's going to increase your 0 to 60 time, aka it's going to increase your Michaelis constant. The interesting thing is the effect that that has on our Lineweaver-Burk plot. Because remember, if we're increasing our Km value, what effect that's going to have is actually decreasing 1/Km. And the easy way to find the Km value was the x-intercept. So if 1/Km is sliding closer to the y-axis, we would expect that -1/Km would slide closer to the y-axis as well. We can still find our -1/Km value as the x-intercept. Its position has just changed. And this leads us to our last prompt question, or at least our last official prompt question. This one asks us how all these changes induced by the competitive inhibitor will influence the Lineweaver-Burk plot. Well, given the new Km value and what you know about Vmax, plot what you would predict for our new Lineweaver-Burk curve. Again, one of the big advantages of a Lineweaver-Burk plot is that two data points make a straight line. So if you want to understand why a competitive inhibitor will increase the slope of a Lineweaver-Burk plot, all you have to do is plot the new line. That said, I do want to take one last look back at Michaelis-Menten plots and see how all of this same information about competitive inhibitors would apply to that kind of plot type as well. Given what you now know about competitive inhibitors and their effect on Vmax and Km, predict how the Michaelis-Menten plot will be changed by the presence of a competitive inhibitor. We know that a competitive inhibitor leaves the Vmax the same, so we would expect that the asymptotic maximum would be unchanged. But we also know that a competitive inhibitor increases the Km value because we are decreasing the efficacy of the enzyme. As a result of increasing the Km value, you notice that the slope of this plot has gotten flatter. So again, Lineweaver-Burk plots and Michaelis-Menten plots may tell you the exact same information, but they literally present it in opposite ways. In this lesson, you saw the ways in which scientists use both Lineweaver-Burk plots and Michaelis-Menten plots to plot the same information, but in very different ways. And you saw that there are advantages and disadvantages to each plot type. On test day, you could see one, the other, or both plot types, so be prepared to answer questions about either or both.